Hi, my name is Neha Kadam, and this is lecture 3 on printed circuit board fundamentals. Table of contents, placement and routing technique continued from the previous lecture. Schematic fundamentals we'll be covering, and traces. Trace reflection. So reflections and matching are closely related to loop antenna theory, but differ enough to warrant their own discussion. So when a PCB trace turns a corner at a 90-degree, a reflection can occur. This is primarily due to the change of width of the trace. At the apex of the turn, the trace width is increased to usually around like 1.414 times of its width, and this upsets the transmission line characteristics, especially the distributed capacitance and self-inductance of the trace, and thus resulting in the reflection. As we know, not all PCB traces can be straight, and so they will have to turn corners. Most software systems they give some round effect on the traces. Now here, rounding at 45 degree, this figure on the left shows rounding at 45 degree, typically reduces overall trace length. This practice frees board area, reduces current loops, and improves both electromagnetic capability emission and immunity. And also it looks better. If PCB traces are turns at acute angle, then there is a higher possibility of an acid trap forming during etching on the inside of the angle. An acid trap causes over etching, which can be a yield issue in PCBs with small trace width. So here, figure shows a progressively better technique of rounding corners. Only the last example here in this figure maintains constant trace width and minimizes the reflection compared to these two. So this is the best design of best way of giving the turn at a corner. Now mechanical placement concerns. Components should not be located in keep-out areas defined by mechanical engineering. Predefined component location for adjustment, heat dissipation, or electrical performance must be considered. Component location must be compatible with any defined height restriction. So here you need to remember that never put parts in an area where they can interfere with mechanical structures in the final assembly. Also, note where some component need to be located for access after final assembly. The physical parameters of the PCB must be inconsistent with the mechanical requirements of the electronic system. Tolerance must be optimized to provide the best fit between the board size, shape, and thickness, and mechanical hardware used to mount the board. So here, when you design the PCB, before you place a component on the PCB, you will have you need to make sure that exactly where your mounting holes and edge connectors should go, and what kind of mechanical enclosure you need to fit on your board. Understanding these variables will affect both the size and the shape of your board. Moving on to the next slide. Now comes the electrical characteristics. Introduction. Here you see a battery connected to a light bulb, and mainly in this picture, the purpose of this picture is to show the direction of signals. So here you can see the electron flow is going from the negative side, turning on the light bulb, and the return signal is going into the positive side. So the same return path of the signal should follow on the PCB. So signal traveling on the PWP, This is same as a printed circuit board, or you can say that printed wiring board. Traces also return to their source on adjacent return planes. So it is important to establish that all signal must have a complete path to function. This establishes the purpose of the return plane in a PCB. So this is one of the important electrical characteristics. Now moving on to the next slide. This is a view of two adjacent layers of copper in the layout program. Blue is one layer and magenta. Uh, so here, magenta is the other layer. They are separated by a dielectric. How far away from each other the two layers are will make a difference on the effective noise cancellation of the signal. The closer together the two layers are, the more noise cancellation it will be established. This is due to the capacitance that is created. Also, if the trace has a blank area underneath it in the ground plane, then the electrons must travel farther and may interfere with the return path of another signal, and this creates noise. Now moving on to the next slide. So here, this is the return paths. It says return paths critical for high-speed signal. So here, one of the keys in determining the optimum printed circuit board layout is to understand how and where the signal return currents actually flow. So most designers only think about where the signal current flows and ignore the path taken by the return current. So to address this concern, we must understand how high frequency current flow in conductor. So here first, the lowest impedance return path is in the plane directly underneath the signal trace, since this provides the lowest inductance path. This also produces the smallest current loop area possible. Secondly, due to the skin effect, I hope you remember the skin effect. In the skin effect, when a high frequency, when a circuit is working on a high frequency, then the current mainly passes from the surface of the conductor, and it does not pass through the whole, it does not cover the whole conductor. So, so back to this. Secondly, due to the skin effect, high frequency currents cannot penetrate a conductor, and therefore at high frequency, all currents in the conductors are surface current. And this effect in the PCB will occur at all frequencies above if you are working on 30 megahertz for 1 ounces copper layer. Therefore, a plane in a PCB is really two conductors, not one conductor. And there will be a current on the top surface of the plane, and there will be a different current or no current at all on the bottom surface of the plane due to the skin effect. Now, here there is another major concern in the high-speed signal is the electromagnetic capability. And this problem occurs when there are discontinuities in the current return paths. And these continuities cause the return current to flow in a larger loops, which increase the radiation from the board as well as increase the crosstalk between adjacent traces and causes waveform distortion. In addition, constant impedance PCBs, the return path discontinuity will change the characteristics impedance of the trace. So here we need to make sure that we have a short return path in the PCB when you are designing the circuit. And the other thing we can do is using a ground shielding. Uh, as you might know, ground metal plate greatly attenuates electric field. Stray electric fields, including radio frequency fields, can effectively effectively shield it using a metal enclosure that surrounds sensitive components. When various components are separated into different enclosures, the shielding also prevents interference between components. So this worked in the past with slow signals. However, with fast signals switching speeds, this method tends to just create antennas out of the intended shield. But if you're working for the slow signals, then you can use ground shielding. So here in this diagram, it shows the same thing to use the shortest return path. And if you create the long return path, then it will have capacitance in between. Now moving on to the next slide. Now here it shows the vertical cut of a 16 layer PCB. If you count this, this is a 16 layer PCB. This is not a best view, but it does show how to maximize signal layers and keep enough ground plane layers available. If a power plane is one consistent power rail, for example, like 3.3 volts, it can be used as a return plane. If power is broken up into many power levels, for example, 1.8 volts, 2.2 volts, 3.3 volts, or 5 volts, etc., then it should be considered a signal layer and not used as a return plane. Now comes the schematic fundamentals. Here it shows the sheet size refers to the physical dimension of the piece of paper that your technical drawing is created on. These are the common sheet sizes which I mentioned here. I think in right now you guys working on 8.5 cross 11. Now moving on to the next slide. Schematics are usually drawn with the following consideration. So these four things you should keep in mind when you draw the schematic in general. Inputs should be on the left hand side and outputs should be on the right hand side. Power rails should be or represented on the top side, and ground should be on the bottom. So this schematic representation reflects all the four things, where the power is on the top and ground is represented at the bottom, and input is on the left, whereas output is on the right. Now further, here is an example circuit which is divided into three different circuits: amplifier, filter, and amplifier. Uh, so when you work on a PCB software, you can basically use hierarchical representation, and which I'll show you in the next slide. So this is the hierarchical schematic representation. So you can break your circuits like this, and then you can put it under these kind of symbols. So this basically shows the amplifier. This is also an amplifier. And this symbol used here is the filter. So if you click on when you design it on the PCB and you click on these symbols, then you can actually see the whole circuit. And this is very useful. And the reason why, because this will uh, creates your design more very short and very clean. Now, how to do it on KiCad? So on the left hand side on your schematic page on the KiCad, here is this symbol create hierarchical sheet. So if you click here, then this kind of window will appear, and you can name the file, name this file depending upon your schematic. And when you change the name, uh, Just click on OK, and then if you and then your this sheet will be created, and when you right click on this sheet, then you can actually you can enter your you can actually paste your the whole circuit which you want to fit into this block. Now some design rule check. So the KiCad software, it basically checks for unconnected pins, unconnected nets, power and ground shorts, and many other connectivity issues. And it does not check for circuit functionality. It does not check for good schematic design. Pin connection information such as did you put the pins in the right spot on the symbol? Fundamental design issues, all these things it does not check. So you have to make sure when you design the circuit on the KiCad that you keep in mind all these points. Now comes the layer stack. So here it shows a 4-layer board cross section, and as you can see here, all these layers are mentioned. So the top and the bottom layers are the solder mask, whereas this layer, second layer, is your top copper, and this light yellow portion is your substrate. All of these are substrates, and in the middle, these are again the copper uh, copper plate inside the PCB. So this makes it a 4-layer board: 1, 2, 3, and 4 copper layers. So this makes up a 4-layer PCB board. Now let's uh, talk about the traces. So here traces are the electrical wires that connects electronic components within a conductive layer. So here in this example, you can see all these connections. These are traces. Here you see this light green portion, these rails. These are traces. These all are traces. So their function is to connect between 2 points where you want where you want the electricity to pass. Now comes the strip lines and micro strip lines. And what are these? So strip line, this shows the strip line, and this shows the micro strip line. Strip line and micro strip are basically the method of routing high-speed transmission lines on your PCB. Strip line is a transmission line trace surrounded by dielectric material suspended between two ground planes on internal layers of the PCB, which you can see here. Strip line is here, and it's surrounded by the substrate. And microstrip routing is a transmission line trace routed on the external layer of the board. So it is always going to be on the external layer. Because of this, it is separated from a single ground plane by a dielectric material. Now with the transmission line on the surface layer of the board, microstrip routing has better signal characteristics than strip line. Board fabrication is also less expensive with microstrip, since the layer structure of one plane and one signal layer makes the manufacturing process simpler. Whereas in strip line, it can be more complex to manufacture because of its design. As you can see here, it requires multiple layers to support the embedded trace between two ground planes. However, the width of a control impedance trace in a strip line is less than an impedance trace in the microstrip of the same value. This is because of the second ground plane. These smaller traces width enable greater circuit densities, which in turn enables a more compact design. The internal layer routing of strip line also reduces the electromagnetic interference and provides better hazard protection compared to microstrip. Now moving on to the next slide. Now in this slide, this is it shows both microstrip and strip line, and they may need to be connected to internal planes or between layers like this. Here, the trace sizes must be chosen based on the current required in the circuit. Note that these are the rule of thumb type of equation. Specific material and other design factors such as operating temperature will affect the result. Now here, trace may need to change layers to connect to components to avoid traces on the surface of the PCB. So connecting traces with vias. So here you see these are the two vias shown here in this PCB structure. So traces should be sized large enough to handle the current expected. The most common variable in trace design is the width, but the trade-off is an increase in capacitance. Sometimes the physical dimension of the trace becomes very critical, such as when routing digital signals. The length may need to be kept the same to reduce the timing error, or for high frequency like radio frequency signal, the trace may need to be impedance matched to the source. And here these traces are connected through the via. These two vias you see, these are the copper layer connected through the via. Now it shows the conductive layer are used, usually plated rather than left or as bare copper. So here you see this is your gold plating shown here, and here also this is another layer which is a tin plating can be used. So this plating can add corrosion resistance and improve solder joints. So that's why these conductive layers are used in the PCB. Now this slide talks about the a via. A via is an electrical connection between conductive layers and allows an electrical current to pass from one layer to another. So we have already seen this in the uh, last to last slide, and here we can visually see from this example of the PCB that this is the via, and there are two types of via, or normal via or a visible via, and blind via for connecting traces or planes. Now we'll go to the next slide. So here an example of a normal plated through via on two-layer board is given. So this is our two-layer board. You can see this is the copper strip, and this is also a copper strip, and in between is the substrate. This light yellow portion is the substrate, and this is called your via on a two-layer board. And this is called plated through via. Now an example of a blind via on a four-layer board. So this is a four-layer board of layer 1, layer 2, layer 3, and layer 4. So here this is also a via because this is your copper. This is a conductive path in your PCB, and here also this is the conductive path, and this portion here is your blind via. And in this particular example, the through via is also mentioned. So here you see a through via is also mentioned, This green portion is your solder mask. Solder mask is here, and then this is the copper strip, copper layer, and this is a through hole, through via, and this is the blind via in a 4-layer port. Now here, as you see in the picture, that two traces are shown. Here, this trace is wider compared to this trace. This is a narrow trace. So the trace width also vary, and it depends upon the amount of current it carries, and depending upon that, the size may vary. Uh, so here it is written same. Some electrical properties are varied with the physical properties of the trace, which may be important to the designer. For example, a wide trace can carry more current than a skinny trace. So this trace might carry more current compared to the current in this narrow trace. Now moving on to the next slide. This picture show the trace width. This is a copper layer trace width, and the distance between two copper layer is called trace to trace distance. So this is a PCB port design, and this is a copper layer, and it's the same thing, and this is the basically the zoom form of this portion. So it says this is the trace width. It can be determined this way, and the distance between these two traces is called your trace to trace distance. Now comes the trace resistance with relationship to the width. So copper traces here are utilized to connect one element node to another node. The shape of these traces determines one very important aspect of a PCB, the characteristics, inductance, capacitance, and ultimately the characteristic impedance. Resistance is generally ignored as most designs do not carry more than several milliampere of current, and the result can often be negligible. But however, if you have to calculate the trace resistance, then you can calculate it by this formula, where W stands for trace width in inches and L stands for trace length in inches. Now, this slide explains the current handling is related to proportionally to the trace resistance and hence the resistance. So here the example is given: if 25 amps per inch of width for 1 ounce copper, uh, which means around 0.0014 inches thick. Or in another way, we can say that 1 inch per 25 amps will have 0.015 inches, which is basically the trace width divided by the trace current capacity. So in PCB, if you're using the FR4 material, probably that is the one of the most common PCB material used by manufacturer today, and has a permeability range normally from 4 to 5, but 4.5 is often used as a typical permeability. So when you design the PCB, make sure that make sure that you check the manufacturer to determine what material they utilize, and the associated permeability, because that will change the current handling capability. Now this slide basically talks about the traces on the exposed layer. Top and bottom copper are called microstrip. It's the same thing. It's saying this is the microstrip, and in between it can have capacitance as well as inductance, which is shown here. Trays have capacitance and inductive reactance. And traces have these electrical properties that need to be considered when they are designed. An advanced designer will use these properties to their advantages. So here, trace capacitance, it depends on the width and dielectric constant of the substrate. And trace inductance depends mostly on on the length of the trace. And trace resistance, as we have already seen, depends on the thickness of the trace and length. Now here, this slide shows how you can calculate the capacitance, and this is the formula you can use, where H is the separation between the planes, and it is represented here. A is the area of common plate, and ER is the permeability. So this way you can calculate it. And moving on to the next slide, and this is another way to calculate it, inductance and capacitance. So you can use these formulas to determine uh, these parameters: inductance, capacitance, and impedance. Now, here are some of the useful circuit design rules. First, design effective return planes and arrange them correctly in both stack up to avoid a noise problem. Group signal lines of similar logic families together. Avoid termination of logic outputs directly into the transistor bases. Terminate unused logic pins with a resistive pull-up or pull-down resistor. So we have discussed this already. Do not tie signals outputs together. Where possible, divide complex logic function into a smaller combinational logic section. So these are all things we have covered, and this is kind of summary of it. So now is the end of the lecture. Thank you everyone for uh, watching the lecture.